This is a solutions video for chapters 7 through 9, test spring of 2014. There was 54 points possible, and I think the high score is only missing 1, but I did give 2 points back to everybody. So on number 1 here, a key here is to look and see what type of data is being measured, and it looks like it's proportions. And then the next question is how many samplings did they take, and there's just 1 sample. So this is a hypothesis test for 1 proportion. And our null hypothesis here is that it is 13% come from single parent homes. The alternative is not 13%. There is no strong language to make you think it's greater than or less than, so it should be a two-tailed test. I was lenient on the grading, so you didn't have to have that, but just so for the final, if you're studying for that, I'll be a little more particular looking for the wording if it's one tail, two tail, greater than, less than, or not equal to. So we found our z-score here, and it's 1.82, and then we looked that up on our z-table, and we noticed that this tail has 0.0344. So there's about a 3.5% chance that you would get this much difference by random chance. And since it's a two-tail test, we actually double it to make it 0.0688. And that is bigger than 0.05, so we would fail to reject or do not reject the null hypothesis. Now, hypothetically, if you made this one-tailed and this was just 0.0344, then I would accept, yeah, you could reject then. I accepted both of those answers. But just so you know, based on the wording and how this is done, this is the way it should be. So if you didn't quite get it that way, just be prepared in the final for that. So do not reject. There is not significant evidence the population proportion is different than 13% of households. All right, and then on, oops, fix that a little bit. There we go. And then on the second part here is just a 95% confidence interval. Oh, I'm sorry, type 1 and type 2 errors. So the type 1 would be the reject the null, say the population proportion is not 13%, but it really is, and you were wrong. The type 2 error would be to fail to reject the null hypothesis, say the population proportion is 13%, but it's really something different. All right, and then on number 2, this is a single sample with means. So we have a hypothesis test with 1 mean. So our null is that the engine life is 220,000. The alternative is that it's greater than 220,000 because we have this greater than. We're testing that claim. And we calculate our t-statistic here. And we get a t-stat of 6.45, which is very large. And if you look that up on your t-table, and since there's sample size of 10 cars, so if we looked in row 9, 6 is like way over here. It's way off the charts, which means our p-value also would be kind of off the charts here. Almost 0% chance of that happening by randomness. So our p-value is about or approximately 0. And since that's less than 0.05, we would reject the null. And we do have significant evidence the average engine life is more than 220,000 miles. And then sorry about that. Let's see if we can fix this a little bit. Yeah, all right. Jumping around there. Okay. And then we needed to calculate a 95% confidence interval for this. So X bar is 243,450 plus or minus, and then this 2.262. If I go to row 9 of that t-table again, and I look for the 95%, the 95% is this very bottom or middle row, and I go up to 9, and there it is, 2.262. So that's my t multiplier if I want to do a 95% confidence interval with 9 degrees of freedom. And there's our sample standard deviation and sample size. So we would be 95% confident the true mean engine life is somewhere between 235,224 and 251,676. And the question is, does it contain 220,000? The answer is no, which backs up like, no, there's a difference here from what our sample says and what we thought was going on. Number 3 is 2 proportions. We're checking to see if the proportion of smokers in these 2 age groups are the same or not. So our null is that they are the same. The alternative is that they're not the same, not equal to. So this is a two-tail again. We calculate our z-stat here to be 1.54. If we look that up on the z-table, we get 0.0681. If we double it, gets us up to 0.1236. Either way, both are much greater than 0.01, which is our significance level up here. So we do not reject the null. We don't have significant evidence the proportions of smokers is different. And then a 99% confidence interval, we use this 2.575, which is what we use for our Z multiplier. And if we go to our formula sheet here, you can actually get that right there. 2.575 is 99%. And then there's the confidence interval formula right there. And so we would be 99% confident the true difference in proportions is somewhere between negative 0.027 and positive 0.1 or positive 10.7%. And do you think there's a significant difference? The answer would be no, because 0 is in that interval. So it's possible there's no difference, which again backs up our hypothesis test. Number 4 is checking the difference between two means. Our null hypothesis is these two brands have the exact same average burn time. And the alternative is that the brand X is greater than, it says that right there, that has a longer burning time, so it'd be greater than. One-tailed test. Here's the formula for that t-test, and the calculation gives us a t-score of 16.045, which is crazy high. Again, that puts our p-value at almost 0, which is much less than 0.05, and that means we would reject the null, and we do have significant evidence the mean burn times is greater than for brand X is greater than brand Y. And the second part here is a little new question. We want to compare the variation between the two. So this has got a 1.4 standard deviation, a 0.8 standard deviation. The question is, are those significantly different? And our null would be like they're the same, alternatives they're not. We calculate the F statistic, which is just, if you look at your formula sheet, I'll show that again. So for the formula sheet, right here on the hypothesis test side, here we are. There is our F stat. It's just the, oops. Let me scroll down a little bit here. There it is. So it's the larger standard deviation squared divided by the smaller standard deviation squared. And so if we go back to that, I give you the two standard deviations and you square them, find the ratio, and it's 3.06. And if we looked that up on our F, like our F calculator in StatCrunch, it would give us a p-value of 0.0009, very small, which means we would reject the null and say there is a significant difference in the variation of the two brands or deviation in the two. I accepted either of those language. So you got to mention that it's you're analyzing the variances or deviations. Number 5, a lot of people had trouble remembering how to write the null and alternative here. Remember, this is paired or dependent data. So our null is that there's going to be no difference. And these are the same people being tested twice. So this is what we call paired data. Our null is that that difference will be 0. The alternative is it's going to be greater than 0, that the gymnastics teaching is effective. And t is d bar minus mu sub d. So the average difference, it says right, the mean difference was 0.157. And our assumption was that there was going to be none, so that's a 0. And we get a t statistic of 4.62. If we look in, there's 7 gymnasts. If we look in row 6 for 4.62, again, off the charts here, that means yes, there is significant difference here. It's very rare that you get this much difference just by random chance. So we are going to reject the null. There is significant evidence the training did improve the scores. And then the type 1 and type 2 errors for that, we say, yeah, reject, say the training did improve, but it really didn't. Type 2 is to say we failed to reject, say, nope, didn't make any difference or significant difference in it, but it really did. Number 6 is they tested, the researchers like, wow, I wonder if going to rock concerts hurts hearing, and they said, yes, there was significant evidence of hearing loss, which means they rejected the null. And they rejected this at the 0.01 level, so that'd be way out here in this tail. So the question is, would they make the same decision at 0.05 and 0.1? The answer would be yeah. If it's rejected, if the p-value is less than 0.01, it's obviously also less than 0.05 and also less than 0.1. And the last question here is a new one, which was the confidence interval for variation or standard deviation. And this comes right off your formula sheet here. And their n is 20 and s was 2.7. And then we just have to look at our chi-squared table for the chi-squared left and right. And since the sample size was 20, we look in row 19, and we're looking for the 99%. So I'm going to go to that chi-squared table. Row 19 is right here, but we want 99%, which means there's a 0.5% to the left, which would be this column, and a 0.5% to the right. So we'd actually use the first and last columns, because that's 0.5% each tail, 99% in between. So this would be the chi-squared left, right there, 6.844, and this would be the chi-squared right, 38.582. Put those right in there. So we get a 99% confidence interval for the variance is here, and I did count that right, but I was looking for the standard deviation, which means you take the square root of everything. So really we are 99% confident the true deviation in these washing machines is somewhere between 1.9 and 4.5 years. And that's it. Hope this video helps, and good luck on your final, or if you're watching this to prepare for your test this semester.